We're going to evaluate this problem. I think I put the problem on the exercises, so you can check if you have the file. You can check the file. I've put in I think in the last exercise. So this is chapter 1 problem, which I want to review, at least just to prepare for the quiz next week. So this is what we have: the uniform distributed load, which is this BC on the structure BC. We have the distribution loads is 3.2 kilonewton per meter, and then we have the conditions that the pin A, or the joint A, is, you can see that it has a roller. It has roller. So it's only the vertical reaction, right? So the first question is again very basic. It's reaction at A and C. And if you see something that has to do with the distributions, the first thing you need to do, if you want to make sure all the reactions, we are going to simplify these distributions and make it into the resultant, the total resultant on this distribution. And there will be many types of distributions. This is, I would say, a rectangular type, which this is going to be perfectly in the middle. Perfectly in the middle. So it will be in the center. It will be in the center. And we know all the distances. The height is 2 meters. The distance from A to B is 1.5. From B to C is 2.5. So we all know all the distance. So I think the best way to approach this is we are going to write another diagram, but maybe simplified the whole diagram. So I will write here, this is AB, maybe up until there, and then that is BC. Okay. So this will be 1.5. This will be, the total is 2.5, but I will write, since I will make a total resultants for the distribution force, I will make this will be 1.25. This will 1.25. Okay, 25 divided by 2. And the force is basically 3.2 multiplied with 2.5, or 5 over 2. So 1.6 multiplied by 5 is 8, right? So it will be, we will have an 8 kilonewton. So these steps for drawing this free diagram and then calculating all the equilibrium, this is equilibrium process. So we are going to take all the external force and reaction force and then make equilibrium. Okay, and besides of that, we have a reaction on A, or let me write A here, B, and C, and we have a reaction here, only vertical reactions. Okay, only vertical reaction for the AY, because A has a roller, so we could see that it can move freely horizontally, so we could have only reaction on the vertical, right? And then we have both reactions on C, so maybe drawing like that, CX and CY, and all the directions you can assume based on your experience, or maybe you can just write randomly for the directions, and you will notice the correct directions when you compute the number. Okay, I think all done. So what's next is we are going to take this equilibrium into the statics. Okay, statics, the overview because we want to know the reaction between the point A and point C, then we could take directly the sigma moment, and I will just start with C, and I will make all the clockwise to be positive. Okay. So AY multiply with 4 meter, right? And then that is clockwise, and then minus 8 kilonewton multiply with 1.25, and this will be equal to 0. From here we get the AY. So AY, I think I can simplify 4 and 8, so it becomes 2. So we have 2.5 kilonewton. Let me write with black. 2.5 kilonewton meter. Oh, sorry. It should be meter. Meter is cancelled, right? I forgot. Okay, so AY we get, and then after we get the moment, all the rest will be we can expect to get from this axial force. So first maybe the Fy equals 0, and taking this AY plus CY equal 8 kilonewton. So 2.5 plus CY. So CY is 5.5. I think I will make it smaller to make it more space. And since the horizontal force is, there is nothing there, so we could maybe we could write first the x equals 0, and then we can say that the reaction at Cx it's equal to 0. And all the assumption for the directions, they are I think make sense because this result is positive. Well, you could see that because there is only one axial force on this side, so it would make sense that there will be a reaction from the bar, right? So to cancel the 8 kilonewton. Okay. And then this is the first question, right? The first question, we get all AY, CY, and CX. And then the second question is determine the internal resultants at the cross sections of AB and BC. So we are going to find the axial force, the shear force, and then the moment, the bending moment. So we can start from the picture here. Maybe I will draw the picture, maybe like that. I'm taking this V1, F1, and then this will be M1. And then what else do we have? So we want to know first is perhaps the F1. So we could write first the equilibrium for the Fx1 to denote this is for the first bit in between AB. This will be equal to 0. And I think we have the AY, right? AY is, I forgot, AY is what? 2.5, right? So AY is here. So this is A, This is AY. AY 2.5 kilonewton. Okay, now we have usually you are expected to have this kind of problem. So you have a bar that is not in a horizontal or vertical. So we have a diagonal position like this. But remember, we still have the distance here. Right? We still have the height. We still have this 1.5. So we could use some ratio and to get at least the ratio for trigonometry, because we are expecting this f1 to be in a component of sine and cosine, right? So we could see we have 2 and 1.5. So we have this triangle. Okay. And if we multiply by, let's say by 2, we are going to have 4 and 3, and of course this will be 5. So this is a 3, 4, 5 triangle. 1.5, 2. Okay. So, or let me write here just to help out. So we have, so this is 1.5, this is 2, and we see that if we multiply by 2, this is perfectly 3, 4, and this should be 5, right? Okay. So we are going to have, this is, maybe let me write here to make it longer. And then let me write that this F1 has a component. So this one will be sine, so this will be 4 over 5 F1. This will be 3 over 5 F1, right? Okay, so this would be, maybe start from the easiest one, the y first. It's 3, 4, 5. Okay. We could do this, or we could make the AY to become the same with the F1. Let me try that. This could work, but if we work the other way around, should be resulting the same. So suppose that we have, this is 3, 4, 5, and I want to have the AY here and AY there. So this will be the cosine, this will be the sine, so this will be the 4 over 5 AY, 3 over 5 AY. I think this will be, faster, because if we did the previous one, we need to recalculate for the shear force. So why I choose this to have this component, because this will be in line with the F1, this will be in line with the V1, so we could get everything. I think this will be a correct approach. The previous one also okay, but I think the problem, we need to make another sine cosine component, but should be the same. Okay, so this will be let me just write everything. So this will be V1 is equal with
3 over 5. AY is 2.5. This will be equal to 1.5. And then F1 is equal minus 4 over 5, right? This will be negative 2 kilonewton. So F1 is going to be in the opposite directions, which means it's not a tensile, it will be compression. It will be compression. So we get a compression here. And then the moment, I forgot the moment. The moment, since there are no clear distance, we can just assume based on this x1. So we could just write that as our answer. So let's just write this as x1 distance. So sigma moment at this, let's say this is the point 0. Let's say that's the point 0. Taking that as equal to 0, make it positive on clockwise. So 3 over 5, right? 3 over 5, 2.5, multiply with x1, or a kilonewton, and then minus, what else do we have? We don't have anything left, right? Only that. And also the moment itself, the M1. Okay. So M1, we get, this will be 1.5 x1 kilonewton meter. So we get this is for the AB. So this is for the member AB. For member AB. So basically, just to make sure that we are with the same idea. So y and x is becoming this axis and that axis. So we simply just move the axis. So sometimes, problem in statics or in mechanics of materials, we can move the force based on the geometry, or we can move the axis. So it depends on your preference which one you move, as long as it is the same. So let's say we can move like making this as an axis and this is axis, or the force, it can be in this way. Okay. That both okay, both okay. Okay, we still have one more additional internal resultants for the BC. So BC is that way. So we are going to write here, let's say a so let's say this is a 4 member BC. And since we are going to take a new distance, which are going to define by the x2, and since we are able to calculate the c, so you have to, like if you want to compute this, you have two choices. You can choose this side, or you can choose this side. Both are correct. Both are correct. If you choose this side, you will have a force that is working on this AB, which you get from this F1. Okay, you can choose this one and get this F1. Or you could use this and use the reaction force at the C. Both should be incorrect calculation. So you can choose two points. You can choose this or this. The difference is the result. If you choose this left, the distance is x2. If you choose this, then the distance will be this minus the x2. Okay. I hope that is going to be okay with that. And I will choose to make it variations. Let me choose this is the C. Okay. And this will be and also we have the 3.2 kilonewton per meter that we need to multiply for the resultant force. So let me write here first. This is going to be 25 minus x2 meter. Okay. And we are going to have expecting that the new resultant will be in the center of this member. Okay. This will be 3.2 multiply with 2.5 minus x2 kilonewton meter. Oh, kilonewton, sorry. We already multiplied. And then this side here, both of them, will be the half of the 2.5 divided by 2, right? Okay, both of them are the same distance. And what else we have? This is becoming the F2, and we are going to write the opposite direction with the questions. It will be V2, and we are going to have this moment here, the bending moment M2. Okay, I think everything. Oh, I forgot the C. CY is 5.5, so CY is going upwards. So we have here CY equal 5.5 kilonewton. Now I think everything are in picture now, so we could write the equilibrium. So first write sigma fx equals 0, sigma fy equals 0. And I think there are no horizontal force, so F2 eventually will be 0, right? And then the vertical will only have the CY, right? And the loads. So CY, or let me write, maybe going a little left a little bit. So CY, or 5.5, is equal to or let me write maybe V2 plus 5.5 is equal with that. Maybe make it a little bit going to the left. Okay. 3.2, 2.5 minus x2 kilonewton. So V2 we can multiply for a while. 3.2. Let me multiply this. Just checking. 1.6 is 8. 8 minus 5 is 2.5. So 2.5 positive minus 3.2 x2 kilonewton. So V2 we get, and then the sigma moment, and let's write this is, let's say, maybe D. Okay, so take on D equals 0, and this will be positive for clockwise. So we can write the M2 and then plus 3.2, 2.5 minus x2 squared over 2. And then the rest is 5.5 is minus 5.5, 2.5 minus x2. Let me get in through that. Okay, so M2, this is equal 0, is equal, this will be 1.6. So this will be 4, and I think you can just use calculator to calculate this. It has a squared. Well, also you could check if you use the left part here using the F1. So let me write here. So I think I will leave this to you. Just expand the squared and then just algebraically solve. I think I could use this to make it this. Okay. We could have also the other way around. So we could check the B. And you are going to set this as a, since this is going to be we could use the opposite direction, the F1 equal 2 kilonewton. And then using the x2 as the distance. And then as usual, you can bring the component here using the same ratio triangle, and you can make this sine cosine component, and you will get the same result. This should be the same with this, but since we are not sure on the x2 because it's a variable, then it could be a new different quadratic equations that is going to be essentially should be equal with this. Okay, I think that is this problem for the 1/420. Okay. Any questions so far? I think should be okay, right? This type of question. Okay. Now another thing that I want to show is wait a minute. Oh, I think this one. I just want to show you the plot, okay? And since this is just an exercise, we could do some quick plot using many software. You can use Excel or Google Sheet. And I just tried this a few minutes ago, just a quick quickly just put all the numbers and then just take some formula. Let me show you the result. So wait a moment. Let me go through here. Okay, this is how it looks like. Okay, and after some scaling, and I make the scale, the step is exactly 0.001, and you can see that at 0.001 it is precisely at the 200, and this means that you can directly get the modulus of elasticity, which is 200. Find of this should be, so this is MPa, megapascal, so multiple with this, it should be 200 gigapascal, which is, I think, quite okay. And then plot the curve and use the 0.2% offset method to determine yield strength of this material. So the yield strength could be determined, and this is, I think, for most of these the alloy material, especially steel. So the 0.2% will be here, okay? 0.002, the strength. So at this point, you can plot and make the line parallel with this. You make this line here, and then put all, and you get some point into the curve. And this point will be your yield strength. And you can just estimate how much is it. You are given the data. And I think for our case, as long as you understand how to read the curve and know how to get the data and the formula, I think you should be okay for the general courses. But for future references, I hope you can do some analysis for the data. So I just make it a very, very quick formulations, the stress and strain based on the loads and delta. You could get that results. Okay. But this is not in the chapter 1, this is chapter 2. But I think for chapter 2, we are still having a more review, I think next week. Maybe just one more exercise. I will try to, okay, how about this 2.86? I don't think we have time to do this, but I just want to show you at least how the workflow, okay, how the workflow. And see the questions. So it has some structure, and it is mentioning the bracket time. Remember that yesterday we developed that there are two different shear modes, or we could say the direct shear has two different modes. The first one is single shear, the second one is double shear. The differences is going to be the double shear. We are going to have triple layer like this, and the single shear we only have like two. Okay. And based on that, the formulation also different. The formulation also different for this shear stress. And the rest of the problem, aside from that, can be solved through our normal calculations, like we did in the chapter 1 and also a little bit in chapter 2, like the statics part, all the equilibrium part, that is statics. So we need to do that first. After we get some evaluations, like for example, some reaction forces and etc., then we can see other questions. And this question, it has this shear, and also it has the allowable, which means that this is going to be related to safety factor. So if you are still struggling on chapter 1, the statics part, the statics will be carry over for the whole chapter in this course. So it's not like a separate topic. So if you are not doing very well in the first one, it will be very difficult if you pass through. Because if you see the typical questions in the course, it will take over or carry over all the statics part, which they assume you get it on the first part. So I hope at least in chapter 1 should be, you should be able to at least familiar and master it. Okay, so we have this. I think we can start to look at what we have. So first of all, we could simplify the problem for the schematic diagrams by looking at where is the external force. This is the external force, right? This bar, right? It's having, like it has the load, which means that first you could take this bar in exclusion, maybe draw again, and then we can have this, and have distance, have load. So I think it's equilibrium, right? Equilibrium process. So we could go for making that part. And it is also mentioning the distance. So we could have, this is going to be so I think I will just give you like a very few pointers here just to let you know how it works. A, and then let's say this is B, or maybe not B, maybe E, because B is on the upper side. So maybe this is E, and this is C, and we have this is the W. And we neglect the weight of the platform. So the bar, the platform AC, we ignore. Okay, ignore. This is going to be A, and A is 0.8 according to the information. This one is 0.5. And then on A, we could imagine that there are some forces that are pulled on the rod. We could say that this is F1, F2. And to get the stress, we can calculate the area first. So area 1 is, we can calculate based on the rod. What is the rod? D2, D1 and D2. So maybe area for rod. So they are considering the same diameter. So let me just write A2. Let me just write A2 first. Pi. This is D2 squared over 4. Right, and you get some number. And then area for pin. Okay, because we are going to also calculate the pins. And we expect to calculate the shear on the pin, right? So this will be area for pin. This is the P squared over 4. So we get both area. And then we get the equilibrium
So the equilibrium, we can get the ratio for the whole force and distance. Okay, so let me write here. This is A, this is B. So sigma moment, let's say at A equals 0, and taking this positive. So W A, and then minus A plus B F2 equals 0. So solve this and we get W over F2 is A plus B over A, right? Or in this case, this will be, plus 0.5 divided by 0.8. So 1.3 over 0.8. And then we have the allowable stress, which is 85. So sigma allowable, this is going to be used by F over A, right? And since the A will be the same A with our calculations from the W over F2, so this is W over F2 is equal with this. So the maximum, so this is allowable. So the maximum weight, let me write here that this is the maximum weight, will be the ratio W over F2 multiplied with the sigma allowable multiply with the A2. Or here is the F allowable is sigma allowable multiply with the area. Okay, so the ratio will be, and then this we can calculate how much. And then in the pin, we can also calculate the same thing. So this is for the rod, for the pin, the maximum weight for the pin, so max weight for pin. This is for a rod. Same thing, we have the ratio, calculate with this sigma or this tau, the tau allowable, multiply with the area for pin, and then you get the number here. Okay. And based on the calculations, later we can see that the weight for the rod is less than the weight for the pin. So we are going to use this as maximum allowable weight. Okay. this is attendance for today's class. Okay. Do you need homework? or not? Maybe after the quiz, okay? After the quiz to help. And I can add the homework as a activity point.